Alright, welcome back everybody. In this video we're going to be discussing concepts from section 8.9 of AP Calculus, volume with the disk method revolving around the X or Y axis. So in this lesson we're going to start our study of solids of revolution. Now, what is a solid of revolution? A solid of revolution is when we take a region and we're going to revolve that region around some line, the x-axis, the y-axis, some other line, and what happens is when we spin that region around a line, it forms a three-dimensional solid. Okay, and we're going to have two specific methods that we're going to use to find these volumes in this course, the disk method and the washer method. And we're going to start by looking at the disk method. The disk method, we use that anytime one boundary, and it can be either the upper boundary or the lower boundary. This doesn't make a lot of sense to you yet. Or the right boundary or left boundary when we're revolving around the y-axis. As long as any boundary of the region is the same as the axis around which we're revolving the solid, then we're going to use the disk method. If the axis around which we're revolving to create the solid is not a boundary of the region, then we do not use the disk method. We're going to use the washer method instead. Okay, so we're going to start by looking at solids that we create when we revolve a region around the x-axis. So take a look at this curve right here. Imagine taking this solid and revolving it, spinning it around the x-axis to make a three-dimensional solid. Okay, so try to visualize what happens when we do that. It's like almost like we make like a weird kind of cup, cup-shaped or vase-shaped object here. So try to picture what that three-dimensional solid looks like. Now, when we do that, what happens is, each slice perpendicular to the axis of rotation forms a shape. It forms a cylinder. Okay, if I take a slice out of this solid after I've made it, it forms a cylinder. And if we look at this cylinder, we can use that cylinder to develop our model for how we're going to find the volume by using the integral to add up all these short little cylinders. So imagine we've built a solid by spinning this around the x-axis. We take two very thin, very close together blades and chop a piece out of that solid, and this is what the piece looks like, where this distance was the value f of x, because that formed the radius of the cylinder if we look at it from the side. And if we take that piece and flop it down flat on the table, it forms we're getting this circular shape here where the function formed the radius. So in order to find the volume of this cylinder, the volume of any cylinder is pi r squared times h. The radius here for this solid of revolution is f of x, and the thickness is dx. And so this expression right here represents the volume of this solid that we've created by revolving the region around the x-axis. We've created a disk. All right, those cylinders are just disks. If we integrate that from one end of the region to the other, say take the integral from a to b of pi times f of x quantity squared, we have the volume of the solid that we're looking for. All right. So outside of that, important things we need to concern ourselves with, if we're going around the x-axis, everything needs to be in terms of x in our integrand. We're using the x-coordinate of the left endpoint of the region and the x-coordinate of the right endpoint of the region, and our integrand and differential need to be in terms of x. If we're revolving around the y-axis, okay, then everything's going to be in terms of y. Notice the difference here. We were talking about the x-coordinate of the left endpoint and right endpoint. And when we're talking about the y-coordinates, we're talking about y-coordinate of lower endpoint and upper endpoint, because we're spinning something around a vertical line instead of a horizontal line. Okay? As long as you keep this in mind, that when we're going around the x-axis, everything's in terms of x. When we're going around the y-axis, everything's in terms of y. So let's go ahead and we'll look at a few examples here and set them up and go ahead and find the volumes using the disc method. So our first example, we're going to find the volume of the solid generated by revolving the region bounded by y equals x squared and the x-axis and the lines x equals 2 and 5. We're going to go around the x-axis. So we'll go ahead and make a quick little sketch. We've got y equals x squared. We've got the x-axis. And we've got the lines x equals 2 and x equals 5. And so our region looks like this. And we're spinning this region around the x-axis, which means that the distance from this curve to the axis is going to form the radius of our solid. So in this case, the radius is going to be x squared. Now we can set up our integral in order to find the volume of this solid. So we've got pi times the radius squared from one end of the region to the other, x equals 2 to x equals 5. And there's our setup that we're going to use to find the volume of this solid. Now at this point, I have choices. I can integrate this by hand, or I can integrate it using my calculator. It's not too hard to go ahead and integrate this by hand. In this case, we've got, x to the 4th. We can just go ahead and take the antiderivative of that. Gives us x to the 5th over 5. And then we can evaluate that. I don't know that I want to take 5 to the 5th power a lot in my life, but 5 to the 5th power is 3125 over 5, so that's going to be 625 minus 32 over 5. And there's the volume of our solid. We could do that using our calculator. Could go ahead and use my numerical integral. I've got pi times the integral of x to the 4th with respect to x from 2 to 5. And if I do that, I get this decimal value, which we can double check is the same as pi times 625 minus 32 over 5. Should be the same as. And they are. All right, let's go ahead and we'll move on to example 2. In example 2, we're going to find the volume of the solid generated by revolving the region bounded by these curves around the y-axis. And so the first thing that I'm going to do is I'm going to draw a quick little sketch of this x equals natural log of y. Looks like that. The y-axis, y equals 2, y equals 7, look like this. So this is our region that we're revolving. And we're revolving it around the y-axis right here. Come on. So this boundary is a boundary of the region. The axis of rotation is a boundary of the region. And so we're going to use the disc method. And our radius of rotation is perpendicular to this axis that we're spinning it around. So it's the distance between x equals natural log of y and the axis of rotation. And so our setup here is going to look like pi times the integral from one end of the region to the other, bottom to the top, 2 to 7, of the radius squared with respect to y. Everything is in terms of y because we're going around the y-axis. And so I'm going to go ahead and calculate that using my calculator. I've got pi times the integral of the quantity natural log of y, quantity squared, with respect to y, from 2 to 7. And that gives us our volume of 34.793, where 34.792 is also acceptable. Now this one I had to do with a calculator because we don't know how to integrate the quantity natural log of y, quantity squared. So we kind of had to do that with a calculator here. All right, example 3, final example of this lesson. All right, so we're going around the y-axis here, and this problem requires you to do a little bit extra in the process. First, I sketch my region. I've got y equals x squared. Got the y-axis, and the lines y equals 1 and y equals 4. Now, there's two regions that are formed here. We're only going to use one of them because if I take this region and revolve it around the y-axis, it's going to give me the same solid as if I took this region right here and revolved it around the y-axis. Even though my parabola is a little lopsided here when I drew it, it's going to create the same solid. So we're only going to use one of those regions. But in order to go around the y-axis, I need to solve this equation for x. So I take the square root of both sides, and I get x equals plus or minus the square root of y. But this is the plus side of the curve. This is x equals positive square root of y. So that's what we're going to use as our axis of rotation here, the distance between the x-axis and the graph x equals square root of y. And so our integral is going to look like pi times the integral of square root of y, quantity squared, with respect to y, from one end of the region to the other, bottom to top, since we're going around the y-axis. 1 and 4 are our limits of integration. And so this one I can do by hand. The antiderivative is y squared over 2. And so we end up with pi times 8 minus 1/2. So 15 pi over 2, which is approximately, if you want a decimal answer, 15 pi over 2 is 23.562. 23.561 also acceptable. And I would have gotten the same thing if I had done the numerical integral there. So that's how the disc method works. We've got a region. We're rotating it around a line. That line that we're rotating it around forms the entire boundary of one side of the region. Then we find the radius of the disc by finding the distance from the axis of rotation out to the curve that generates the region. And then we integrate that from one end of the region to the other. When we're integrating in terms of y, we're going from the bottom of the region to the top. When we integrate in terms of x, we're going from the left-hand side of the region to the right-hand side. So that's it in a nutshell, the disc method. All right, see you all next time when we go into section, oh gosh, I've lost track of what section we're on, section 810, where we're going to do a little bit more with volume using the disc method. All right, everybody, have a good rest of your day, and we'll see you next time. Bye-bye.